The relationship between cosmic web structure and the intergalactic medium reveals one of the most complex and dynamic aspects of cosmic evolution, where vast quantities of gas exist in various phases and temperatures throughout the filamentary network. The intergalactic medium, containing roughly 90% of all ordinary matter in the universe, exists primarily as a tenuous plasma of hydrogen and helium distributed along the cosmic web's filaments and within the voids between them. This gas is not uniformly distributed but follows the underlying dark matter scaffolding, creating a complex ecosystem where gas densities, temperatures, and ionization states vary dramatically depending on location within the web's hierarchy. In the densest regions where multiple filaments converge, the intergalactic gas becomes shock-heated to temperatures exceeding 10 million degrees, glowing brightly in X-rays and creating the intracluster medium that fills galaxy clusters. Along individual filaments, the gas maintains intermediate temperatures of hundreds of thousands to millions of degrees, warm enough to be highly ionized but cool enough to avoid the extreme conditions found in cluster core. Within cosmic voids, the gas remains much cooler and more diffuse, creating vast reservoirs of pristine material that has experienced minimal processing since the early universe. The thermal history of this intergalactic gas is written in its absorption signatures against background quasars, creating a forest of absorption lines that astronomers can decode to map the cosmic web's three-dimensional structure and understand the physical processes that have heated and ionized the gas over cosmic time. Recent observations with space-based X-ray telescopes have begun to detect the warm-hot intergalactic medium directly, confirming theoretical predictions about the thermal structure of the cosmic web and providing new insights into how baryonic matter traces the underlying dark matter distribution. The interaction between this intergalactic gas and the galaxies embedded within it creates a complex feedback loop where star formation and black hole activity within galaxies heat and enrich the surrounding medium. While the properties of the intergalactic gas regulate the rate at which new material can accrete onto galaxies to fuel continued star formation, the phenomenon of cosmic web detachment and the formation of satellite systems around massive galaxies illustrates how the hierarchical nature of structure formation creates complex dynamical environments that profoundly influence galaxy evolution. When smaller dark matter halos fall along cosmic web filaments toward more massive halos, they experience tidal forces that can strip away their outer layers of dark matter, stars, and gas, transforming them from independent galaxies into satellite systems orbiting within the gravitational influence of their larger neighbors. This process, known as tidal stripping, operates over timescales of hundreds of millions to billions of years, gradually removing material from infalling satellites and depositing it into the diffuse stellar halos that surround massive galaxies. The efficiency of tidal stripping depends critically on the orbital properties of the satellite, the mass ratio between the satellite and its host, and the internal structure of both systems. Satellites that approach their hosts on radial orbits experience more severe tidal forces than those on more circular trajectories, while satellites with lower central densities are more susceptible to disruption than their more concentrated counterparts. The cosmic web plays a crucial role in determining these orbital properties, as the direction and velocity with which satellites approach their hosts is largely determined by the geometry of the filaments along which they fell. However, recent studies have shown that these correlations are even tighter when the large-scale environment is taken into account, with black holes in different cosmic web environments showing systematically different relationships between their masses and host galaxy properties. Black holes in massive elliptical galaxies located at the centers of galaxy clusters tend to be more massive than those in similar galaxies found in lower density environments, while black holes in void galaxies often appear undermassive relative to their host bulges. This environmental dependence suggests that the cosmic web regulates black hole growth through multiple mechanisms, including the rate at which gas is supplied to galaxy centers, the frequency of galaxy mergers that can trigger black hole growth, and the large-scale gas flows that can either fuel or starve central black holes. The orientation of black hole spins also appears to be influenced by the cosmic web, with some studies finding that black hole spin axes tend to align with nearby cosmic web filaments. This alignment could arise from the preferential accretion of material that flows along filaments, carrying angular momentum information from large scales into the central regions of galaxies. The feedback from actively accreting black holes in the form of powerful jets and radiation can in turn affect the large-scale environment by heating the intergalactic medium and suppressing star formation in nearby galaxies. This creates a complex feedback loop where the cosmic web influences black hole growth, while black hole activity modifies the properties of the cosmic web itself. Understanding these connections requires simulations that can simultaneously resolve the small-scale physics of black hole accretion and the large-scale dynamics of cosmic structure formation, a multi-scale problem that represents one of the greatest challenges in computational astrophysics. The phenomenon of cosmic web reconstruction through gravitational lensing has emerged as one of the most powerful techniques for mapping dark matter directly, bypassing the need to rely on luminous tracers like galaxies that may not perfectly trace the underlying matter distribution. When light from distant galaxies travels through the cosmic web toward Earth, its path is bent by the gravitational fields of intervening dark matter structures, creating subtle distortions in the shapes and positions of background galaxies that can be measured with precision. By analyzing the statistical properties of these distortions across large areas of the sky, astronomers can reconstruct the three-dimensional distribution of dark matter with unprecedented accuracy, revealing filaments, nodes, and voids that might be invisible in galaxy surveys. This technique, known as weak gravitational lensing, has revealed that the cosmic web is even more filamentary than suggested by galaxy distributions alone, with dark matter forming thin, dense filaments connecting more massive halos. The most dramatic demonstrations of cosmic web lensing come from observations of galaxy cluster mergers, where the collision of two massive dark matter halos creates tidal streams and bridges of dark matter that can be mapped directly through their lensing effects. These observations have provided some of the strongest evidence for the existence of dark matter itself, showing that the gravitational effects are spatially separated from the luminous matter in ways that are difficult to explain with modified gravity theories. Recent advances in lensing surveys have enabled the detection of individual cosmic web filaments through their weak lensing signatures, confirming theoretical predictions about the filamentary nature of dark matter structure. The next generation of space-based telescopes with their superior image quality and sensitivity promise to map the cosmic web through gravitational lensing with exquisite detail, potentially resolving individual dark matter subhalos within larger structures and testing theories of dark matter physics on scales previously inaccessible to observation. The combination of lensing observations with other probes of cosmic structure, including galaxy surveys and cosmic microwave background measurements, is beginning to provide a complete three-dimensional picture of how matter is distributed throughout the universe and how this distribution has evolved over cosmic time. The discovery of cosmic web streams and their role in galaxy formation represents one of the most significant recent advances in our understanding of how galaxies acquire the gas needed to form stars over billions of years. Traditional models of galaxy formation assume that gas accretion occurred through a hot, spherically symmetric halo. but detailed simulations have revealed that much of the gas actually flows along cold streams that follow the cosmic web's filamentary structure. These streams can penetrate deep into galaxy halos without being shock heated, delivering cool gas directly to galaxy centers where it can efficiently form stars. The existence of cold streams helps explain how massive galaxies can maintain high rates of star formation over extended periods, as the streams provide a continuous supply of fresh fuel that bypasses the hot halo gas that would otherwise prevent further accretion. Observational evidence for these streams is beginning to emerge from deep spectroscopic surveys that can detect the faint emission from gas flowing along filaments, as well as from observations of extended gas halos around star-forming galaxies. The properties of these streams depend critically on the cosmic web environment, with galaxies located at the intersections of multiple filaments more likely to experience multiple stream accretion than those situated along single filaments. The transition between cold stream accretion and hot halo accretion appears to depend on both galaxy mass and cosmic web environment, with more massive galaxies and those in denser environments more likely to experience hot accretion. This transition has profound implications for galaxy evolution, as it determines not only the rate at which galaxies can grow, but also their chemical evolution and morphological development. Galaxies that accrete gas through cold streams tend to maintain extended disks and continue forming stars, while those that switch to hot accretion often develop more spheroidal morphologies and reduce star formation rates. Understanding the physics of stream accretion requires sophisticated simulation that can resolve both the large-scale flow of gas along cosmic web filaments and the small-scale processes that determine whether this gas remains cold or becomes shock-heated as it approaches galaxy halos. Freych's gallows. The statistical properties of cosmic web connectivity reveal fundamental insights into the nature of dark matter and the physics of structure formation that extend far beyond simple measurements of clustering strength. The cosmic web can be characterized as a complex network where galaxies and dark matter halos serve as nodes connected by filamentary edges, and the statistical properties of this network encode information about the underlying cosmology and the processes that govern structure formation. Network analysis techniques borrowed from other fields, including sociology and biology, have been applied to cosmic structure to quantify properties like the distribution of node degrees, the number of filaments connected to each node, clustering coefficients, the tendency for connected nodes to share common neighbors, and path lengths, the minimum number of steps required to connect distant parts of the network. These network properties exhibit characteristic signatures that depend on the fundamental parameters of cosmology, including the densities of dark matter and dark energy, the amplitude and spectral index of primordial density fluctuations, and the masses of neutrinos. For example, universes with different dark matter properties produce cosmic webs with different connectivity patterns, while variations in the initial conditions affect the typical lengths and masses of filaments. The evolution of network properties over cosmic time also provides insights into the growth of structure, with the cosmic web becoming increasingly connected as smaller structures merge to form larger ones. Recent studies have found that the cosmic web exhibits small world properties similar to social networks, where most nodes can be connected through relatively few intermediate steps despite the vast distances involved. This high connectivity has implications for the transport of matter, energy, and information throughout the universe, potentially affecting processes like the spread of chemical elements produced in stellar nucleosynthesis and the propagation of radiation from the first stars and galaxies. The development of new statistical tools for characterizing cosmic web topology represents an active area of research, with machine learning algorithms being developed to automatically identify and classify different types of cosmic web environments based on their local connectivity patterns. The temporal evolution of cosmic web structure provides a unique window into the physics of dark energy and modified gravity theories, as different models make distinct predictions about how the web should grow and evolve over cosmic time. In the standard cosmological model, dominated by cold dark matter and a cosmological constant, the cosmic web grows hierarchically, with smaller structures forming first and then merging to create progressively larger ones. However, the rate of this growth slows over time as dark energy begins to dominate the universe's energy budget, eventually bringing structure formation to a halt as the accelerated expansion of space overwhelms the attractive force of gravity. Alternative models of dark energy, including those where the dark energy density changes over time or where dark energy interacts directly with matter, predict different evolutionary histories for the cosmic web. Some models suggest that dark energy might have been weaker in the past, allowing more rapid structure formation at early times, while others propose that dark energy might strengthen in the future, eventually leading to the dissolution of even gravitationally bound structures. Modified gravity theories also make distinctive predictions about cosmic web evolution, often predicting enhanced growth rates on large scales where the modifications to general relativity become important. Observational tests of cosmic web evolution require measurements of structure at different cosmic epochs, which can be achieved through surveys that observe galaxies at various distances and thus look back to different times in cosmic history. The comparison of cosmic web properties at high redshift early times with those observed locally recent times provides one of the most direct tests of dark energy models and alternative gravity theories. Recent observations have confirmed that the growth of cosmic structure has indeed slowed over the past few billion years, consistent with the influence of dark energy, but precision measurements of this growth rate could reveal deviations from the standard model that would point to new physics. The next generation of large-scale structure surveys will measure cosmic web evolution with unprecedented precision, potentially distinguishing between different models of dark energy and testing the fundamental assumptions underlying our understanding of cosmic acceleration. The cosmic web, the invisible skeleton of the universe, is at once a scientific reality and a poetic vision. It shows us that the cosmos is not a scattering of stars but a woven tapestry, not a void but a structure, not a silence but a symphony. Its filaments connect galaxies across billions of light years, its voids sculpt the geometry of space, and its evolution records the history of time itself. It reveals the hand of dark matter, the push of dark energy, and the echoes of quantum ripples from the beginning of everything. It is the largest structure we know, yet it resembles the smallest patterns in nature, uniting the cosmic and the human in a single design. To study the cosmic web is to study ourselves, for we are born of its filaments, children of its nodes, products of its flows. To contemplate it is to recognize that we are not alone, but connected, not isolated, but threaded into a universal fabric. And to imagine its future is to understand both the fragility and grandeur of existence, a universe expanding, a web thinning, but a pattern enduring, etched forever in the memory of space. The cosmic web is not only the skeleton of the universe, it is also its poetry, its memory, and its promise. The universe is not an empty void scattered randomly with galaxies. Rather, it is structured in a way that resembles a colossal three-dimensional web, with threads stretching across unimaginable distances and knots where matter has gathered to form the largest cosmic structures we know. This vast architecture, known as the cosmic web, is often described as the invisible skeleton of the universe because it shapes the distribution of galaxies, clusters, and dark matter into an intricate network that defines the very layout of cosmic existence. To grasp this concept, one must begin with the origins of matter in the aftermath of the Big Bang. Roughly 13.8 billion years ago, the universe began as a hot, dense plasma of particles, energy, and radiation. As it expanded and cooled, tiny fluctuations in density, Quantum ripples magnified during inflation seeded the uneven distribution of matter. These variations were exceedingly small, only a fraction of a percent different from one region to another, but over cosmic time gravity amplified them into the vast web-like structures we now observe on scales of hundreds of millions of light years. At first glance, the distribution of galaxies across the night sky seems scattered and chaotic. But when astronomers map them in 3 dimensions using redshift surveys, a remarkable pattern emerges. Galaxies are not isolated, but instead clumped together in filaments and sheets that intersect at dense nodes. These nodes form galaxy clusters, giant metropolises of galaxies bound by gravity, while the filaments act like bridges of matter connecting one cluster to another. Between these luminous strands lie vast cosmic voids, regions where very few galaxies exist, creating the illusion of bubbles in an expanding foam. What makes the cosmic web particularly fascinating is that it is not composed only of the visible matter we can detect in the form of stars and galaxies, but primarily of dark matter, the mysterious substance that neither emits nor absorbs light yet accounts for about 85% of the universe's matter. Dark matter provides the gravitational scaffolding upon which normal matter gathers, and without it, the universe would look entirely different. In fact, computer simulations that include dark matter show that when the laws of physics are applied to the conditions of the early universe, matter naturally arranges itself into a cosmic web. This insight confirms that the universe's large-scale design is not arbitrary, but the inevitable outcome of fundamental physical laws. Observing the cosmic web directly, however, is a formidable challenge because most of its substance is invisible. Astronomers rely on indirect methods, such as detecting the faint glow of hydrogen gas illuminated by distant quasars, or using gravitational lensing, where light from faraway galaxies is subtly bent by the mass of dark matter to trace the hidden filaments. These techniques reveal that the web stretches across billions of light years, making it the largest structure in existence. Within these filaments, galaxies form and evolve, their growth influenced by the cosmic environment that surrounds them. Galaxies in dense filaments tend to be larger and more active in star formation, while those in isolated voids evolve more quietly, showing that the cosmic web not only arranges matter, but also regulates the life cycle of galaxies themselves. To imagine the scale of this structure, consider that our own Milky Way is just one of hundreds of billions of galaxies in the observable universe, and yet it lies along a filament connected to the Virgo cluster and beyond, as part of the Laniakea supercluster, an enormous region spanning 520 million light-years. This supercluster itself is but a node within an even larger network, hinting that there is no ultimate largest structure, only progressively greater patterns woven by gravity. What is most striking is that the cosmic web resembles patterns found in nature on far smaller scales. Networks of neurons in the brain, the mycelium of fungi, or the branching of rivers and lightning, suggesting that the universe follows universal principles of organization regardless of scale. So, the invisible skeleton of the cosmos thus embodies not only astronomical grandeur, but also a profound philosophical idea. That order arises from simplicity, that complexity emerges from basic rules, and that the universe, despite its enormity, echoes structures we can recognize in our everyday world. Oh, yet the cosmic web remains dynamic, not frozen in time. As the universe expands, filaments continue to stretch, clusters grow heavier as they accrete galaxies, and voids enlarge as matter drains into surrounding structures. Over billions of years, this evolution sculpts the universe's appearance, with regions of high density becoming ever denser and regions of emptiness becoming empty. If dark energy, the mysterious force driving cosmic acceleration, continues to dominate, the filaments may eventually thin out and galaxies will recede from one another beyond the limits of visibility, leaving future observers stranded in cosmic isolation, unable to perceive the grand web that once connected everything. For us, living in the present epoch, we exist at a privileged moment when the cosmic web is both richly structured and still observable, allowing us to study the universe's grand design and contemplate our place within. Understanding the cosmic web is not merely an exercise in mapping galaxies. It is a way of uncovering the fundamental blueprint of the cosmos, the architecture that guides matter, energy, and time. It is a reminder that while we may seem small against the vastness of the universe, we are threads within the same web, connected to the largest and most mysterious structure in existence, great. I'll now continue with paragraph 2 and paragraph 3, each around 1,000 words, written in the same continuous detailed flow without headings. The idea that the universe is structured like a web was not obvious to early astronomers. For centuries, human beings thought of the cosmos as a set of crystalline spheres or a boundless void sprinkled randomly with stars. It was only in the 20th century, with the advent of large-scale galaxy surveys, that the true complexity of cosmic distribution began to reveal itself. When telescopes became powerful enough to collect spectra of distant galaxies and measure their redshifts, astronomers could map their three-dimensional positions in space rather than merely seeing them projected as points of light on the sky. One of the first breakthroughs came with the CF, a redshift survey in the 1980s, which showed that galaxies were not scattered evenly but instead formed immense structures, including what became known as the Great Wall, a sheet of galaxies stretching over 500 million light-years in length. This was a startling revelation because until then, most scientists assumed galaxies might clump in clusters but not extend into such gargantuan arrangements. The Great Wall, and later the Sloan Great Wall discovered in 2003, provided direct evidence that the universe contains coherent patterns on scales that defy ordinary imagination. These discoveries compelled theorists to revisit cosmological models and ask how such structures could arise naturally from the physics of the early universe. Simulations provided an answer. When computers modeled the growth of structure under gravity using dark matter and initial fluctuations from the Big Bang, they produced networks of filaments and clusters that looked strikingly similar to what redshift surveys were uncovering. The match between observation and simulation grew stronger with time, culminating in projects like the Millennium Simulation, which charted billions of particles of dark matter across a virtual universe and revealed a web-like tapestry stretching from one end of the computational box to the other. Such models show that the cosmic web is not a random coincidence but a natural outcome of cosmic evolution, dictated by the invisible hand of dark matter and the expansion of space. Within this web, galaxies are like beads strung along filaments, forming where gas cools and condenses at the densest intersections. The nodes of the web correspond to galaxy clusters, where the gravitational pull is so strong that hundreds or thousands of galaxies are bound together, while the filaments act like cosmic highways along which material streams into the clusters. Observations of galaxies confirm this dynamic picture. Astronomers can trace how galaxies align themselves along filaments, how they flow into nodes, and how their shapes and star-forming activity depend on their environment. Those in crowded filaments often experience frequent interactions, mergers, and bursts of star formation, whereas those drifting in cosmic voids evolve in relative solitude. The voids themselves are as important as the filaments, for they represent regions where the density of matter is far below average, sometimes containing just a handful of galaxies in volumes spanning hundreds of millions of light years. These voids expand faster than the denser regions because there is less gravity to slow them down, and in doing so, they push matter toward the walls and filaments, accentuating the web-like structure. Thus, the cosmic web is shaped not only by attraction but also by repulsion. Gravity pulls matter into clusters, while the underdense voids push matter outward, carving the cosmic skeleton. On human scales, the cosmic web is almost impossible to visualize fully because it operates on lengths that dwarf the mind's ability to grasp. Yet astronomers have made creative attempts to render it visible, using artistic simulations, computer graphics, and observational data to create maps that resemble a three-dimensional spider's web spun across billions of light years. These maps reveal that the universe has no center and no edge within the observable limit. Instead, wherever you place the observers, the web extends outward in all directions, a testament to the cosmological principle that the universe is homogeneous on the largest scales. Even though locally it is intricately structured, this duality, the coexistence of order and randomness, simplicity and complexity, defines the cosmic web as both a scientific object of study and a source of wonder. It demonstrates that from tiny fluctuations in the primordial plasma, gravity wove a structure that now encompasses everything we see, including ourselves. The cosmic web is not simply a background against which galaxies exist. It is the framework that determines their existence in the first place. Delving deeper into the cosmic web, one finds that its importance extends beyond structure alone. It is also a key to understanding the interplay between dark matter, dark energy, and baryonic matter, and therefore to unlocking the ultimate fate of the universe. Dark matter, though invisible, forms the backbone of the web. Without it, baryonic matter, the ordinary matter that makes up stars, planets, and humans, would never have had enough gravitational clumping power to form galaxies. In the early universe, photons coupled tightly to baryonic matter, preventing it from collapsing efficiently under gravity, but dark matter, interacting only through gravity, could begin clustering much earlier. These dark matter clumps became gravitational wells into which baryonic matter later fell, igniting the processes of cooling, star formation, and galaxy assembly. This sequence explains why galaxies and clusters trace the distribution of dark matter so faithfully. But dark matter is not the only mysterious player. Dark energy, which drives the accelerated expansion of the universe, shapes the cosmic web by stretching it apart. On smaller scales, gravity dominates, pulling matter into filaments and nodes. But on larger scales, dark energy thins out the web by accelerating the expansion of voids. Over billions of years, this tug-of-war sculpts the cosmic landscape. If dark energy continues to dominate, the filaments will become increasingly isolated, and clusters will stop feeding on fresh material, leaving galaxies to age and fade in cosmic loneliness. Thus, the cosmic web is not static but evolving, and its ultimate unraveling may hold clues to the destiny of all matter. To probe this delicate balance, astronomers use a variety of observational techniques. One of the most powerful is weak gravitational lensing, which measures the subtle distortions of background galaxies' shapes due to intervening dark matter. By mapping these distortions across the sky, scientists can reconstruct the distribution of mass, revealing the web's hidden filaments even where no galaxies shine. Another technique relies on quasar light shining through intergalactic hydrogen gas, producing absorption features known as the Lyman alpha forest. These absorption lines, when studied in detail, trace the density fluctuations of diffuse hydrogen in the filaments, offering a way to map the web at high redshifts when the universe was younger. Both methods confirm that the web exists not only nearby but also across cosmic time, stretching back billions of years. Computer simulations remain vital companions to observations, allowing scientists to test different models of dark matter and dark energy against the observed cosmic web. For example, warm dark matter models predict fuzzier structures with fewer small filaments, while cold dark matter models reproduce the sharp interconnected web we see today. The close match to cold dark matter simulation strengthens the case that dark matter is cold and slow-moving, although its true nature, whether it is made of weakly interacting massive particles, WIMP, actions, or something else entirely, remains unknown. Regardless of the details, the cosmic web serves as a cosmic laboratory, a vast experiment in which the interplay of matter, energy, and geometry is recorded in the structure of space itself. But the significance of the cosmic web goes beyond physics. It touches on the philosophical and aesthetic, inviting us to ponder why the universe organizes itself into such patterns. The resemblance between the cosmic web and neural networks in the human brain, or the branching of trees and rivers, hints at universal principles of complexity and self-organization. These parallels suggest that networks may be a fundamental way that nature arranges energy and matter across scales. If so, then the cosmic web is not only the skeleton of the universe, but also part of a broader tapestry of order woven throughout reality. To contemplate the cosmic web is to realize that we are not separate from it. We are inhabitants of one of its filaments, born from its densest knots, and destined to share its fate. Our galaxy is not isolated, but a strand in a cosmic network that stretches far beyond what our eyes can see, reminding us that the universe is not a collection of lonely islands, but a deeply interconnected whole. When we think of the cosmic web, it is easy to imagine it as something distant and unrelated to our daily lives, a structure so grand that it belongs only to the realm of astronomers and cosmologists. Yet in truth, it is the very environment in which our galaxy, the Milky Way, exists. And it has shaped not only where we are located, but also how our galaxy has evolved over billions of years. The Milky Way lies in a filamentary region connected to the Virgo cluster, which itself is part of the Laniakea supercluster, an immense structure spanning hundreds of millions of light years. This means that our home is not randomly placed in the cosmos, but situated within the skeleton of the web along one of its many filaments. These filaments act like rivers of matter that feed galaxies, delivering fresh gas that can fuel star formation and growth. Simulations show that galaxies that sit within well-connected filaments receive a steady supply of cold gas, allowing them to form stars over longer periods of time, while galaxies that are stranded in isolated regions may eventually run out of fuel and fade into quiescence. Thus, the cosmic web is not only a map of structure, but also a blueprint for galaxy life cycles, dictating which galaxies thrive and which struggle. Observations confirm this trend. Galaxies in dense environments such as clusters often show signs of recent interactions, mergers, and starbursts, while those in voids evolve more slowly and quietly, forming smaller, less active systems. This environmental dependence highlights the web's role as a regulator of cosmic ecology, a system where position within the network influences destiny. Another aspect to consider is that the web also acts as a channel for the flow of galaxies themselves. Galaxies do not remain fixed in one spot. They move along filaments under the influence of gravity, gradually streaming toward the nodes where clusters form. In fact, the very term a cosmic flow refers to these motions, which can be detected by measuring the peculiar velocities of galaxies relative to the Hubble expansion. Our own Milky Way, for example, is moving toward the Great Attractor, a gravitational anomaly within Laniakea, as part of a larger flow that ties us to the cosmic network. This motion is evidence that the web is not static, but a living, evolving system in which matter is continually redistributed. The study of such flows not only tells us about our place in the cosmic hierarchy, but also provides valuable clues about the distribution of dark matter, since the unseen mass is what drives these motions. The cosmic web thus connects the abstract with the tangible. It links the invisible dark matter to the visible behavior of galaxies, and it links our local environment to the farthest reaches of the observable universe. What is astonishing is that the scale of this structure defies all intuition. A single filament can extend across hundreds of millions of light years, yet it is only a few million light years thick, making it an unimaginably long and slender bridge of matter. Inside these filaments, not only galaxies but also vast reservoirs of diffuse gas reside, forming what is known as the warm-hot intergalactic medium WIMP. This medium is thought to contain a large fraction of the universe's emissing baryons, the ordinary matter that cosmologists know must exist, but that is not accounted for in galaxies or clusters. Detecting the WIM is extremely difficult because it is tenuous and faint, but recent observations using X-ray and ultraviolet telescopes have begun to reveal its presence, confirming that the web is not just an abstract construct, but a physical structure filled with matter. By mapping the WIM, astronomers can complete the inventory of cosmic material and gain deeper insight into how galaxies acquire the fuel they need. This demonstrates that the cosmic web is not only a structure of galaxies and dark matter, but also the reservoir of gas that sustains cosmic evolution. Its importance is therefore both structural and functional, both skeleton and bloodstream of the universe. To understand the cosmic web is to understand how galaxies form, how they live, and ultimately how they die, making it one of the most profound discoveries of modern astronomy. The discovery and study of the cosmic web have also transformed the way we think about scale and hierarchy in the universe. For much of human history, the cosmos was perceived as a layered structure with Earth at the center, or later the Sun at the center, surrounded by stars and planets in a finite arrangement. With the recognition of galaxies as independent systems in the 20th century, our perspective expanded. But it was still easy to imagine galaxies as isolated islands in a vast, empty sea. The revelation of the cosmic web shattered that view, replacing it with a vision of interconnectivity on unimaginable scale. Galaxies are not islands but nodes in a grand cosmic network. Voids are not merely empty spaces but integral components that give shape to the web. And the universe is not a formless expanse but a patterned whole, a lattice sculpted by gravity. This realization echoes in other fields of knowledge as well. The interconnectedness seen in the cosmic web mirrors the structures we observe in other complex systems. Neural networks in the brain, transportation grids in human society, the branching of rivers across landscapes, and even the mycelium of fungi that connect entire forests underground. These parallels suggest that networks may be a fundamental mode of organization, a universal principle that emerges whenever matter and energy evolve under simple rules. The cosmic web, therefore, is not just an astronomical curiosity, but also a profound example of how the universe organizes itself. By studying it, scientists are not only learning about galaxies and dark matter, but also about the nature of complexity itself. Another important implication of the cosmic web is that it forces us to confront questions of scale that border on the philosophical. On human scales, the distances between cities or planets already seem vast. But in the context of the web, even entire galaxies are mere specks strung along filaments like beads of dust. A filament stretching 500 million light years dwarfs everything within it. And yet it is just one thread among countless others in the observable universe. This raises profound questions about significance. If galaxies are small in comparison to the web, and if even the web itself is only a portion of the cosmos we can see, then what does that imply about our place within reality? Far from diminishing us, however, this perspective can be liberating. It reveals that we are part of something unimaginably larger, woven into the very fabric of cosmic structure. The cosmic web connects us through the Milky Way to clusters and superclusters beyond, and through dark matter to the invisible skeleton that underlies it all. This realization expands our sense of belonging, reminding us that humanity is not separate from the universe, but an expression of its most fundamental architecture. From a scientific standpoint, the cosmic web also acts as a testing ground for cosmological theories. By comparing observed structures with simulated ones, scientists can test different models of the early universe, of dark matter, and of dark energy. The remarkable agreement between simulations and observations strengthens the standard model of cosmology known as lambdactum. Lambda cold dark matter, which posits that the universe is dominated by dark energy, lambda, and cold dark matter, CDM, with ordinary matter making up only a small fraction. Yet there are still puzzles. For example, the exact properties of dark matter remain unknown, and small-scale discrepancies between simulations and observations hint that our understanding may still be incomplete. The cosmic web, therefore, is not only evidence for current models, but also a challenge to refine them further. Its filaments and voids hold secrets that may one day reveal new physics, perhaps even leading to a deeper theory that unites the known with the unknown. The cosmic web is, in this sense, both a triumph of modern astronomy and a frontier still waiting to be explored. The cosmic web is more than just a revelation about the structure of the universe. It is a profound shift in how we understand connectivity and hierarchy in nature. For centuries, the cosmos was imagined as layered, finite, or randomly arranged, whether in the form of Ptolemaic spheres or vast, featureless space sprinkled with stars. The leap from geocentrism to heliocentrism and later to the recognition of galaxies as independent island universes expanded our sense of scale. But it was still possible to think of galaxies as separate entities drifting through emptiness. The discovery of the cosmic web shattered that illusion. It showed that galaxies are not isolated, but are instead linked through an intricate, gravitationally sculpted lattice of matter and void. In this view, the universe is not an unstructured expanse, but an interconnected whole, where every galaxy and cluster is a node, every filament a bridge, and every void a cavity that helps give shape to the larger skeleton. So this recognition resonates with patterns we encounter elsewhere in life and science. The resemblance between the cosmic web and the network of neurons in the brain, or the underground mycelium networks that allow fungi to communicate across entire forests, hints at universal principles of self-organization. Even human-built systems, such as the branching of highways or the structure of the internet, echo this networked form. What makes the cosmic web remarkable is that it arises from extremely simple beginnings. Slight density fluctuations in the primordial plasma amplified by gravity over billions of years. From simplicity came complexity, from randomness came pattern, and the result is the largest and most intricate structure ever observed. The scale of the web also forces us to rethink what it means to be large or small. Our Milky Way, containing hundreds of billions of stars, seems impossibly vast when viewed from within, yet on the scale of a filament stretching 500 million light years, it is nothing more than a dust mote along a cosmic strand. Oh ye! A galaxy cluster containing thousands of galaxies is a small knot in the web, and even a supercluster like Laniakea, to which we belong, is just a minor feature compared to the expanse of the observable universe. This realization can be humbling, but it is also awe-inspiring. To understand that we and everything we know are part of a pattern woven across cosmic scales beyond imagination. The web teaches us that scale is relative, and that significance does not vanish with size. It changes perspective. For cosmologists, the web provides a natural laboratory for testing the lambdoctum model, which posits that the universe is composed primarily of cold, dark matter and dark energy. Observations of filaments, voids, and clusters match the predictions of simulations remarkably well, lending strong support to this model. Yet the web also reveals subtle tensions, such as the missing satellites problem, where fewer small galaxies are observed than predicted, or anomalies in void sizes that challenge certain assumptions. These discrepancies drive scientists to refine their models, test alternative theories, and explore new physics such as warm dark matter or modified gravity. Thus, the cosmic web is not just evidence for what we know, but also a probe into the mysteries we have yet to unravel. It is both a triumph of modern science and a challenge to go further. One of the most fascinating aspects of the cosmic web is how it bridges the gap between the smallest beginnings and the largest outcome. The seeds of the web were planted in the first fraction of a second after the Big Bang during a period called inflation. In this epoch, the universe expanded exponentially, stretching quantum fluctuations, tiny variations in density at subatomic scales, into macroscopic imprints across space. These fluctuations were frozen into the distribution of matter and radiation, leaving signatures we can still detect today in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. When cosmologists study the CMB, they see tiny temperature variations, differences of only 1 part in 100,000. But those variations correspond to regions that were slightly denser or slightly emptier than average. Over billions of years, gravity amplified these differences. Denser regions attracted more matter, becoming filaments and clusters, while emptier regions expanded into voids. Thus, the cosmic web we observe today is the direct descendant of quantum fluctuations at the dawn of time. In a sense, the skeleton of the universe is a fossil record of the earliest instance of creation, preserved not in stone, but in space itself. This connection between the smallest scales and the largest structures is one of the most astonishing features of cosmology. It means that the layout of galaxies across billions of light years is ultimately linked to quantum processes in the first split second of existence. To visualize this is to understand the universe as a continuum, where scales are connected in ways that defy ordinary thinking. It also means that by studying the cosmic web, we can test theories of the early universe, such as inflation models, and learn about physics far beyond what we can replicate on Earth. The web is, therefore, not only an astronomical structure, but also a cosmic archive, a record of the laws of physics written across the largest canvas imaginable. Observationally, scientists continue to refine how we map and study this archive. Surveys such as the Sloan Digital Sky Survey SDSS and the Dark Energy Survey DES have charted millions of galaxies, creating three-dimensional maps that reveal the filaments and voids in ever greater detail. Upcoming projects, such as the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, and the Euclid mission, promise to expand this mapping to unprecedented scales and depths, allowing us to trace the cosmic web not just locally but across much of cosmic history. These surveys will enable astronomers to measure how the web evolves with time, how filaments stretch and voids expand, and how dark energy influences the structure's growth. By doing so, they may help resolve key mysteries. Is dark energy truly constant as the cosmological constant suggests, or does it change with time? What are the exact properties of dark matter, and how does it cluster? Are there subtle deviations from Einstein's general relativity at cosmic scales? The cosmic web is the testing ground for these questions because it is where the interplay of matter, energy, and geometry is written most clearly. In addition to these scientific pursuits, the cosmic web has a poetic and even existential resonance. To realize that we live inside a filament connected by threads of dark matter to distant galaxies is to see ourselves as part of something vast and interconnected. It is a reminder that the universe is not random but patterned, that we are participants in a structure that extends beyond sight, and that our very existence depends on the delicate balance of forces that wove the web from the beginning of time. This perspective does not diminish humanity but enriches it, offering a sense of belonging to the largest and most mysterious system ever discovered. The cosmic web is not only a structure of matter, but also a dynamic stage on which galaxies live out their history. To understand galaxies without considering the web is like trying to understand fish without acknowledging the ocean currents. They are inseparable. Galaxies are born, evolve, and sometimes die within the context of the filaments, nodes, and voids that make up the cosmic network. One of the most important processes influenced by the web is accretion, the gradual gathering of gas and smaller galaxies onto larger systems. Along filaments, cold streams of gas flow into galaxies, replenishing their supply of material for star formation. This is particularly evident in simulations of galaxy evolution, which show thin rivers of hydrogen gas feeding young galaxies like veins delivering blood. Without these filaments, galaxies would exhaust their gas reservoirs within a few billion years, leaving them sterile and unable to form new stars. Observations also confirm this, with evidence that galaxies connected to filaments tend to be more massive and more active in star formation than those in isolation. At the same time, the cosmic web provides the setting for violent interaction. In dense nodes where multiple filaments intersect, galaxies collide and merge frequently, triggering bursts of star formation and shaping their structures. These mergers can transform spiral galaxies into ellipticals, alter galactic dynamics, and even feed supermassive black holes. Thus, the location within the web often determines the evolutionary path a galaxy follows. Whether it becomes a quiet, isolated spiral in a void or a giant elliptical forged in the chaos of a cluster. Even galaxy morphology, the visible shape and structure of galaxies, is influenced by the surrounding filaments. Studies have shown that spiral galaxies often align with filaments, their spins oriented along the cosmic strands, while elliptical galaxies are more likely to be found at filament intersections. This alignment is not random, but reflects the gravitational torques and flows of matter within the web. Such correlations demonstrate that the cosmic web imprints its signature, not only on where galaxies form, but on how they spin, grow, and interact. In this sense, every galaxy carries the fingerprint of the cosmic web in its structure and history. Beyond galaxies, the web also hosts immense gas reservoirs that act as connective tissue between systems. The intergalactic medium, IME, mostly composed of hydrogen and helium, fills the filaments and forms a network of diffuse clouds that emit faint ultraviolet and X-ray radiation. This gas is difficult to detect directly, but its presence can be inferred from absorption lines in the spectra of distant quasars. When a quasar's light passes through a filament, specific wavelengths are absorbed by hydrogen atoms, leaving behind a pattern known as a Lyman alpha forest. By studying these absorption lines, astronomers can reconstruct the distribution of gas and trace the filaments even when galaxies are too sparse to mark them clearly. These studies confirm that the filaments are not empty bridges but living rivers of gas and plasma, teeming with the raw material of future stars. The IME also plays a crucial role in the recycling of matter, as galactic winds driven by supernova and active galactic nuclei expel material back into the filaments, where it mixes with pristine gas and eventually accretes again. The cosmic web is therefore not static scaffolding but a circulatory system, channeling matter back and forth across cosmic time. Understanding this cycle is essential to solving one of the biggest puzzles in cosmology, the whereabouts of the universe's missing baryons. While dark matter makes up most of the mass, ordinary matter should still account for about 5% of the total. Yet until recently, nearly half of it was unaccounted for in stars and galaxies. Observations of the WIM warm-hot intergalactic medium in filaments are beginning to close this gap, confirming that the missing matter resides in the web itself. This discovery underscores once more that the cosmic web is not just a backdrop, but a fundamental reservoir of matter and energy, without which the universe's balance sheet would remain incomplete. If the cosmic web defines the universe's structure, then cosmic voids define its contrasts, carving out the negative spaces that make the filaments and clusters stand out in sharp relief. Voids are vast, underdense regions of space, often spanning hundreds of millions of light years, where galaxies are sparse or absent altogether. At first glance, voids may appear to be mere empty spaces, but in reality, they are active participants in shaping the cosmic landscape. Because voids contain less matter, they expand faster than average as the universe grows. This accelerated expansion pushes matter toward the surrounding filaments, deepening the contrast between dense and empty regions. In this way, voids act as the architects of the web's geometry, amplifying the filaments and clusters by pushing matter into them. The importance of voids is increasingly recognized in cosmology, not only as regions of emptiness, but as natural laboratories for studying fundamental physics. Within voids, the density of matter is so low that gravitational effects are weaker and less cluttered, making them ideal places to test theories of dark energy and modified gravity. Because voids expand more quickly, their growth rate is sensitive to the properties of dark energy. By measuring void sizes and dynamics, astronomers can constrain how dark energy behaves, whether it truly acts like a cosmological constant or whether it evolves over time. This makes voids as critical to cosmology as clusters and filaments, turning emptiness into a source of knowledge. Interestingly, galaxies that do exist inside voids provide unique insights into galaxy evolution. These so-called void galaxies often differ significantly from their filament counterparts. They tend to be smaller, bluer, and more gas-rich, with ongoing star formation but less evidence of interactions. Because they are isolated from the dense environments where galaxy mergers are common, void galaxies evolve more slowly and quietly, representing a kind of cosmic control group. By comparing void galaxies with filament galaxies, astronomers can disentangle the effects of environment from intrinsic properties, learning how much of galaxy evolution is driven by location within the web. The study of voids also challenges our perception of scale and distribution. When mapped in 3 dimensions, voids appear like enormous bubbles stitched together by filaments, creating a foam-like structure across the cosmos. This resemblance to soap bubbles or biological membranes once again echoes natural patterns, reinforcing the idea that complexity often arises from simple physical principle. Each void may seem like a barren wasteland, but collectively they account for most of the universe's volume, even though they contain little of its mass. In this sense, the universe is mostly emptiness, structured by thin, dense strands of matter. Such a perspective is both startling and profound. Existence is defined as much by emptiness as by substance, and the largest structures we know are shaped by what is not there as much as by what is. Beyond their scientific role, voids also inspire philosophical reflection. They remind us that absence has structure, that nothingness can sculpt somethingness, and that the balance between void and filament is what creates the universe's beauty. The cosmic web is not just a positive pattern of matter, but a dance between presence and absence, between galaxies and emptiness, between gravity and expansion. In contemplating voids, we confront the paradox of existence itself, that the universe is vast, mostly empty, and yet structured in ways that give rise to galaxies, stars, planets, and life. Without voids, there would be no filaments. Without emptiness, no structure. Without the silent spaces, no cosmic web. The universe, in all its vastness and complexity, is structured not as a uniform sea of matter and energy, but as an intricate network of cosmic architecture that resembles a three-dimensional spider's web stretching across billions of light years. This cosmic web represents the largest scale structure of the universe, a framework so fundamental that it governs the distribution of galaxies, dark matter, and the very fabric of space-time itself. When we peer deep into space with our most powerful telescopes, we observe that galaxies are not randomly scattered throughout the cosmos like stars sprinkled across a dark canvas. Instead, they form a remarkable pattern of interconnected filaments, vast cosmic highways of matter that stretch between enormous voids of near emptiness. These filaments, composed primarily of dark matter with galaxies strung along them like pearls on cosmic strings, create a network so extensive and organized that it challenges our understanding of how such massive structures could have formed in the 13.8 billion years since the Big Bang. The cosmic web is not merely an interesting astronomical phenomenon. It is the very skeleton upon which the entire observable universe is built, determining where galaxies form, how they evolve, and ultimately influencing the fate of cosmic evolution itself. To truly appreciate the cosmic web, one must first understand the scale at which it operates. The largest structures in this web span hundreds of millions of light-years, distances so vast that light itself, traveling at 186,000 miles per second, takes longer to cross these structures than complex life has existed on Earth. The filaments that make up this web are not solid structures like the cables of a suspension bridge, but rather regions of slightly higher density where dark matter and ordinary matter have gravitationally collected over cosmic time. These filaments can be tens of millions of light years wide and contain the mass of trillions of stars, yet they are so diffuse that if you could somehow stand within one, you would perceive it as empty space, with perhaps only a few atoms per cubic meter more than the cosmic average. The nodes where these filaments intersect are even more remarkable, representing the densest regions of the cosmic web where massive galaxy clusters form, containing hundreds or thousands of individual galaxies bound together by gravity. Between these filaments lie the cosmic voids, regions so empty that they contain almost no matter at all, with densities perhaps 1/10 that of the cosmic average, creating bubbles of near nothingness that can stretch across hundreds of millions of light years. The discovery of the cosmic web represents one of the most profound revelations in modern cosmology, fundamentally changing our understanding of the universe's structure and evolution. For much of the 20th century, astronomers believed that galaxies were more or less uniformly distributed throughout space, with perhaps some clustering on relatively small scales. This view began to change in the 1970s and 1980s as astronomers conducted increasingly ambitious surveys of galaxy positions, mapping their locations in 3 dimensions by measuring both their positions on the sky and their distances from Earth. The breakthrough came with surveys like the CFA redshift survey, which revealed that galaxies were arranged in thin sheets and long filaments surrounding vast empty regions. The famous Great Wall discovered in this survey, a sheet of galaxies stretching across 500 million light years, demonstrated that the universe's structure existed on scales previously unimagined. Subsequent surveys, including the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey, mapped millions of galaxies and revealed the cosmic web in stunning detail, showing a universe that looked remarkably like a 3-dimensional foam, with matter concentrated in thin sheets and filaments surrounding enormous bubbles of empty space. The formation of the cosmic web is intimately connected to the mysterious substance known as dark matter, which comprises approximately 27% of the universe's total energy density. Unlike ordinary matter, which interacts electromagnetically and can form complex structures through processes involving radiation and chemistry, dark matter interacts only gravitationally. This seemingly simple interaction pattern actually makes dark matter the primary architect of cosmic structure, as it began clustering under its own gravity shortly after the Big Bang, long before ordinary matter could effectively participate in structure formation. Computer simulations of cosmic evolution, running on some of the world's most powerful supercomputers, have revealed how tiny quantum fluctuations in the early universe, stretched to cosmic scales by inflation, provided the seeds for all subsequent structure formation. These primordial density variations, initially differing from the cosmic average by less than 1 part in 100,000, gradually grew under the influence of gravity. Dark matter, being immune to radiation pressure that would have smoothed out ordinary matter, began forming the first structures when the universe was only a few million years old, creating a scaffolding of dark matter, halos, and filaments that would eventually guide the formation of stars and galaxies. The process by which the cosmic web emerged from the smooth early universe is a testament to the power of gravity operating over cosmic time scales. In the primordial universe, matter was distributed almost uniformly, with only tiny variations in density from place to place. However, gravity is a relentless force that amplifies even the smallest differences. Regions that were slightly denser than average had slightly stronger gravitational fields, which attracted matter from their surroundings, making them even denser. This process of gravitational instability proceeded hierarchically, with smaller structures forming first and then merging to create progressively larger ones. The cosmic web we observe today is the result of this bottom-up structure formation, where dark matter halos formed first, then merged and attracted ordinary matter, which eventually cooled and condensed to form the first stars and galaxies. The filamentary structure of the web arose naturally from the geometry of gravitational collapse in 3 dimensions. While spherically symmetric regions would collapse to form isolated halos, regions that were elongated in one direction collapsed along 2 axes, while continuing to expand along the third, forming sheet-like structure. Similarly, regions elongated along 2 directions collapsed along only one axis, forming the long filaments that characterize the cosmic web. Dark matter halos serve as the fundamental building blocks of cosmic structure, acting as gravitational wells that collect and retain both dark and ordinary matter. These halos form a hierarchy of structures, from the smallest dwarf galaxy halos containing perhaps 1 billion times the mass of the Sun to the most massive cluster halos containing 1,000 trillion solar masses or more. The distribution of halo masses follows a well-defined statistical pattern, with many small halos and progressively fewer larger ones, a relationship that emerges naturally from the physics of gravitational collapse and has been confirmed through both simulations and observations. Each halo represents a local peak in the dark matter density field, a place where the cosmic web has concentrated matter through billions of years of gravitational evolution. The internal structure of these halos is remarkably universal, with density profiles that follow similar mathematical forms regardless of their mass, a consequence of the purely gravitational physics that governs their formation. Ordinary matter falls into these dark matter potential wells, where it can cool radiatively and eventually form stars and galaxies. But the dark matter halo remains the primary determinant of a galaxy's environment and evolutionary history. The nodes of the cosmic web, where multiple filaments intersect, represent the most extreme environments in the universe and host the largest gravitationally bound structures known, galaxy clusters known. These cosmic metropolises contain hundreds or thousands of galaxies swimming in vast oceans of hot X-ray emitting gas, all bound together by the gravity of enormous dark matter halos. The formation of galaxy clusters represents the culmination of hierarchical structure formation, as smaller groups and individual galaxies fall along the filaments toward these intersection points, building up the cluster mass over cosmic time. The intracluster medium, the hot gas that fills the space between galaxies in a cluster, provides a unique window into the physics of structure formation. This gas, heated to temperatures of tens of millions of degrees by the gravitational energy released during cluster formation, glows brightly in X-rays and contains more ordinary matter than all the cluster's galaxies combined. The distribution of this hot gas traces the underlying dark matter distribution, providing one of the most direct probes of dark matter's properties and the process of structure formation on the largest scales. Cosmic voids, the vast empty regions between the filaments of the cosmic web, present a fascinating counterpoint to the dense nodes and filaments. These voids are not completely empty, but contain a sparse population of small, often dim galaxies that have evolved in isolation from the major streams of cosmic matter flow. The environment within voids is so different from that along filaments that it profoundly affects galaxy formation and evolution. Void galaxies tend to be smaller, bluer, and more actively forming stars than their counterparts in denser regions, suggesting that the cosmic web environment plays a crucial role in determining a galaxy's properties. The voids themselves are expanding faster than the cosmic average, growing larger and emptier over time as matter continues to drain out of them toward the surrounding filaments and nodes. Some voids are so empty that they contain less than 10% of the cosmic average density, creating regions where the laws of physics operate in a fundamentally different regime than in the dense environments where most galaxies reside. reside. The study of cosmic voids has revealed that they are not simply empty space, but are dynamic, evolving structures that provide unique laboratories for testing theories of gravity and dark energy on the largest scales. The influence of the cosmic web extends far beyond simply determining where galaxies are located. It fundamentally shapes their properties, evolution, and ultimate fate. Galaxies that reside in different environments within the cosmic web exhibit systematically different characteristics in terms of their masses, colors, shapes, star formation rates, and chemical compositions. This environmental dependence, known as galactic conformity, suggests that a galaxy's location within the cosmic web is one of the primary factors determining its evolutionary history. Galaxies in dense cluster environments often appear red and elliptical, having exhausted their star formation in spectacular bursts, triggered by gravitational interactions with their neighbors. Meanwhile, galaxies in void regions remain blue and actively forming stars, having experienced little gravitational harassment throughout their lives. The cosmic web also channels the flow of pristine gas from the intergalactic medium toward galaxies, providing the fuel for continued star formation. This accretion occurs preferentially along the filaments of the web, creating cold streams of gas that can penetrate deep into galaxy halos and maintain star formation over cosmic time. Observing the cosmic web directly presents significant challenges because much of its mass consists of dark matter, which by definition does not emit or absorb light. However, astronomers have developed ingenious methods to map this invisible scaffolding. The most direct approach involves mapping the positions of galaxies themselves, which act as tracers of the underlying dark matter distribution. Large-scale galaxy surveys have mapped millions of galaxies across significant fractions of the observable universe, revealing the cosmic web structure in exquisite detail. These observations are complemented by studies of the cosmic microwave background radiation, the afterglow of the Big Bang, which carries imprints of the density fluctuations that seeded all subsequent structure formation. Gravitational lensing provides another powerful tool, allowing astronomers to map dark matter directly by observing how its gravity bends and distorts the light from background galaxies. On the largest scales, the cosmic web reveals itself through the subtle correlations in galaxy positions and orientations, statistical signatures that encode information about the underlying dark matter scaffolding, even when individual filaments cannot be directly observed. Recent technological advances have revolutionized our ability to study the cosmic web, with new telescopes and survey instruments providing unprecedented views of cosmic structure. The Planck satellite has mapped the cosmic microwave background with extraordinary precision, revealing the initial conditions from which the cosmic web emerged. Ground-based surveys like the Dark Energy Survey and upcoming projects like the Large Synoptic Survey telescope promise to map billions of galaxies and probe the cosmic web's evolution over the majority of cosmic history. Perhaps most excitingly, radio telescopes are beginning to detect the cosmic web directly through observations of hydrogen gas along the filaments, providing the first direct observations of the ordinary matter component of cosmic structure on the largest scales. These observations reveal that the cosmic web is not a static structure but a dynamic, evolving system where matter continuously flows along filaments toward the nodes, driven by the inexorable pull of gravity and the expansion of space itself. The cosmic web plays a crucial role in our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. The growth rate of cosmic structure depends sensitively on both the properties of dark matter and the nature of dark energy, making precision measurements of the cosmic web's evolution over time one of the most powerful tools for probing these fundamental components of the universe. As dark energy causes the expansion of space to accelerate, it works against gravity to slow the growth of cosmic structure, creating a cosmic tug-of-war whose outcome depends on the relative strengths of these competing forces. By measuring how the cosmic web has evolved over the past several billion years, astronomers can constrain the properties of dark energy and test whether Einstein's cosmological constant provides an adequate description or whether more exotic forms of dark energy are required. The cosmic web thus serves not only as a map of where matter is located in the universe today, but as a fossil record of the cosmic forces that have shaped the universe throughout its history. Understanding the cosmic web requires sophisticated theoretical models and computer simulations that can follow the gravitational evolution of billions of particles over cosmic time. These simulations, among the most computationally demanding calculations ever performed, solve Einstein's equations of gravity in an expanding universe filled with dark matter and ordinary matter. The largest simulations track the evolution of structure formation across volumes comparable to significant fractions of the observable universe, requiring supercomputers capable of performing quadrillions of calculations per second. These simulations have revealed that the cosmic web is a universal feature of structure formation in a dark matter-dominated universe arising naturally from the gravitational instability of primordial density fluctuations. The detailed properties of the simulated cosmic web depend on the fundamental parameters of cosmology, including the densities of dark matter and dark energy, the nature of the primordial fluctuations, and the mass of neutrinos. By comparing simulations with observations, cosmologists can determine these fundamental parameters with remarkable precision and test our understanding of the physical processes that govern structure formation. The fractal nature of the cosmic web represents one of its most fascinating properties, revealing self-similar structure across an enormous range of scale. From the smallest dark matter halos to the largest superclusters, the distribution of matter exhibits statistical properties that repeat at different scales, suggesting that the same physical processes operate throughout the hierarchy of cosmic structure. This fractal character emerges naturally from the scale and variant nature of the primordial density fluctuations and the scale-free character of gravitational interactions. The cosmic web exhibits what mathematicians call a multifractal structure, where different regions have different degrees of clustering, reflecting the complex interplay between gravity, cosmic expansion, and the initial conditions set by inflation. This fractal geometry has profound implications for our understanding of cosmic evolution, suggesting that the processes governing structure formation on galactic scales are intimately connected to those operating on the scales of galaxy clusters and beyond. The connection between the cosmic web and the formation of the first stars and galaxies represents one of the most active areas of current research in cosmology. The earliest stars, known as population 3 stars, formed within the first dark matter halos to collapse in the primordial universe, likely along the primitive filaments of the emerging cosmic web. These first stars were fundamentally different from modern stars, forming from pristine hydrogen and helium gas without any of the heavier elements that facilitate cooling and star formation today. Their formation was governed entirely by the gravitational potential wells provided by dark matter halos, making the cosmic web's early evolution crucial for understanding when and where the first light sources appeared in the universe. The death of these first stars in spectacular supernova explosions dispersed the first heavy elements throughout the cosmic web, seeding the formation of subsequent generations of stars and beginning the chemical evolution that would eventually lead to planets and life. Measuring the properties of the cosmic web with precision requires careful attention to observational biases and systematic uncertainties that can affect our perception of cosmic structure. Galaxy surveys are limited by the brightness and size of detectable galaxies, potentially missing faint dwarf galaxies that might trace the cosmic web more accurately than their brighter cousins. The three-dimensional mapping of cosmic structure requires accurate distance measurements, which become increasingly uncertain for distant galaxies, potentially distorting our view of the web's geometry. Dust extinction within our own galaxy can obscure distant structures, creating apparent voids in regions where cosmic structure actually exists. These observational challenges require sophisticated statistical methods and careful modeling to separate real cosmic structure from artifacts of the observation process. The development of new techniques for measuring galaxy distances, including those based on gravitational wave observations and improved calibration of distance indicators, promises to reduce these uncertainties and provide increasingly accurate maps of the cosmic web. The cosmic web's influence on galaxy formation extends to the smallest scales through its role in regulating the accretion of gas onto galaxies. Computer simulations reveal that gas flows along the cosmic web's filaments in complex patterns, with some gas remaining hot and shock-heated, while other gas streams remain cold and can penetrate directly into galaxy halos. This cold accretion mode appears to be particularly important for maintaining star formation in massive galaxies at high redshifts when the universe was younger and denser. The transition between hot and cold accretion modes depends on both the mass of the galaxy's dark matter halo and its position within the cosmic web, with galaxies at the intersections of multiple filaments more likely to experience hot accretion. The cosmic web also regulates the removal of gas from galaxies through processes like ram pressure stripping in dense environments and feedback-driven outflows that can be channeled along filaments back into the intergalactic medium. Environmental effects within the cosmic web create a complex ecosystem of galaxy types and properties that varies systematically with position in the web's hierarchy. Galaxies in the densest cluster environments often show signs of pre-processing modifications to their properties that occurred before they fell into the cluster, likely while they resided in smaller groups along the cosmic web's filaments. This pre-processing can include the truncation of star formation, changes in morphology from spiral to elliptical shapes, and the stripping of extended gas halos. Intermediate density environments along filaments host galaxies with intermediate properties, while the most isolated void galaxies retain their primordial characteristics longer than galaxies in any other environment. Understanding these environmental effects requires disentangling the complex history of galaxy interactions, mergers, and accretion events that occur as galaxies move through the evolving cosmic web over billions of years. The future evolution of the cosmic web is intimately tied to the nature of dark energy and the ultimate fate of the universe. If dark energy maintains its current properties, the accelerated expansion of space will continue, causing the cosmic web to stretch and dilute over time. Filaments will become increasingly tenuous as matter continues to drain toward the nodes, and voids will expand to encompass ever larger fractions of the universe's volume. Eventually, if current trends continue, the cosmic web will fade away entirely as the universe expands to such an extent that even gravitationally bound structures like galaxy clusters begin to dissolve. However, if dark energy's properties change over time, the future could be dramatically different. Some models predict that dark energy might strengthen over time, leading to a big rip scenario where the cosmic web is torn apart catastrophically, as torn apart, say. Other models suggest that dark energy might weaken or even reverse, potentially leading to a big crunch where the cosmic web collapses back in on itself. The study of the cosmic web has profound implications for our understanding of fundamental physics, providing tests of general relativity and theories of quantum gravity on the largest scales in the universe. The cosmic web structure encodes information about the physics of inflation, the process believed to have created the initial density fluctuations from which all structure emerged. Future gravitational wave detectors will be sensitive enough to observe millions of mergers, providing an independent tracer of cosmic structure that complements traditional electromagnetic observation. The combination of gravitational wave and electromagnetic observations promises to provide unprecedented insights into the connection between the cosmic web and stellar evolution. Advances in artificial intelligence and machine learning are revolutionizing the analysis of cosmic web data, enabling the automated identification of filaments, nodes, and voids in galaxy survey data. These algorithms can process datasets containing millions of galaxies and identify subtle patterns in the cosmic web's structure that would be impossible to detect through traditional analysis methods. Machine learning techniques are also being used to optimize cosmological simulations, identifying the most important physical processes for reproducing observed cosmic web properties, and developing more efficient computational methods. So, deep learning networks trained on simulation data can now predict galaxy properties from cosmic web environment with remarkable accuracy, suggesting that much of the complexity in galaxy formation can be understood in terms of environmental influences mediated by the cosmic web. The cosmic web provides a unique perspective on the anthropic principle and the conditions necessary for the emergence of complex structures like planets and life. The formation of galaxies within the cosmic web requires a delicate balance between competing physical processes, including gravity, gas dynamics, star formation, and feedback. If fundamental constants like the strength of gravity or the mass of elementary particles were significantly different, the cosmic web might not form, or it might have properties that preclude the formation of long-lived stars and stable planetary systems. The hierarchical nature of structure formation within the cosmic web also appears to be crucial for creating the diverse range of environments necessary for chemical evolution and the gradual buildup of heavy elements required for terrestrial planets. Understanding the cosmic web thus provides insights into the broader question of why the universe has properties that allow for the existence of complex structures and ultimately life itself. The study of the cosmic web represents a convergence of observational astronomy, theoretical physics, and computational science that exemplifies modern cosmology's interdisciplinary nature. Progress in mapping and understanding the cosmic web requires advances in telescope technology, detector sensitivity, and data analysis methods combined with theoretical insights from particle physics, general relativity, and statistical mechanics. The computational demands of cosmic web simulations have driven advances in parallel computing and algorithm development that benefit fields far beyond astronomy. This interdisciplinary approach has revealed that the cosmic web is not merely an astronomical curiosity, but a fundamental feature of our universe that connects the physics of the very small quantum fluctuations in the early universe to the largest structures we can observe today. The cosmic web thus serves as a bridge between the microscopic world of particle physics and the macroscopic realm of galaxies and clusters, demonstrating the deep unity underlying the physical laws that govern our universe across all scales of space and time.